The first part of aircraft performance is about the atmosphere. And in the beginning, we need to have a look at the international standard atmosphere. So why we need to study the atmosphere um, when we are learning aircraft performance? This is because the atmospheric characteristics affect the aircraft performance. And for example, let's look at the density role in the atmosphere, how the density affects the aircraft performance. First of all, we can have a look at the lift and drag. They are calculated, for example, lift is half rho v squared times s times CL. So we have density in there. If the density changes, the lift and the drag also changes. And also the air density affects the combustion efficiency, for example, the fuel air mixture in the engine. And if the aircraft is a propeller driven aircraft, so the propeller efficiency is also relevant. Okay, so we know from the thermodynamics there's an ideal gas law. The pressure equals density times R times T. T is a temperature, and R is a gas constant. So gas constant for air is 287 and meter square per second square times Kelvin. So that's a unit for the gas constant. So although it's constant, but R changes slightly depending on the molecular composition of air at a particular location. But in our calculation, we normally use, for air, we use 287 as our the gas constant. Okay, for density, a rho, and the density changes depending on altitude. If it's higher, the density becomes smaller. And also addition of water vapor to air, so which means humidity is increased, reduces air density. So we know the density changes, and also actually everything, density, temperature, pressure changes with altitude. So let's see how the atmosphere is divided into different layers according to their altitude. On the right-hand side, we have a figure, we have a picture about the different layers in the atmosphere around the Earth. Okay, so from the lower part, the first layer is a troposphere. So it is up to 7 kilometers at both poles of the Earth and up to 17 kilometers at the equator. So you can see the troposphere is thicker at the closer to the equator and also thinner at both poles of the Earth. They are not uniform height. That's a troposphere. And above the troposphere, that's a stratosphere, and it's up to 50 kilometer in altitude. And I overlapped an aircraft in the troposphere, so which means the aircraft, our passenger aircraft, operates in this troposphere. And above troposphere is a mesosphere, and that's the altitude is up to 80 and or to 85 kilometers height. And above mesosphere, that's a thermosphere. It goes up to 500 to 600 kilometers, which is really above the ground, high above the ground. And beyond the thermosphere, there's a little air, so we call that space. That's a space we usually define. We know the Earth's atmosphere is organized into five layers. And so now we are going to look at each layer separately in detail. So first of all, closest to the Earth is the troposphere, and we define the top of the troposphere is the tropopause. And the tropopause we already know, and at the equator it's thicker, goes up to 17 kilometers height, and at both poles of the Earth they are about 7 kilometers height. And we're interested in the temperature and the pressure, right? So the temperature decreases linearly within the troposphere, so at a rate of 6.51 Kelvin per kilometer, so that's a decrease, how it decreases. And the pressure decreases exponentially, so about 50% reduction per 5.6 kilometer. So we see the temperature and the pressure decrease following the altitude in the troposphere in a different way. So the temperature decreases linearly, but the pressure decreases exponentially. And also the troposphere features different weather conditions and streams. So, and we can have a look in here. So that indicates the streams within the troposphere. I'm not discussing it in detail, but just let you aware it's featuring weather conditions. The next we have the stratosphere, which is a slightly thinner layer. So the stratopause, which is the top of the stratosphere, and the stratopause altitude is about 50 kilometers in altitude. And the temperature, how the temperature and the pressure changes. The temperature in the stratosphere, so if it's up to 25 kilometers in altitude, the temperature is constant. And from 25 to 50 kilometers, the temperature increases due to the UV absorption in ozone. So the temperature can still increase, although it's at the height. That's because the sun radiation, the UV radiation from the sun. And also the pressure, what happens to the pressure within the stratosphere? The pressure decreases with altitude, and the stratosphere is free of gusts and turbulence because it is characterized by high steady wind or jet stream. Above the stratosphere is the mesosphere. So the mesopause, which is the top of the mesosphere, goes up to 80 to 85 kilometers. And the temperature, how about the temperature change in mesosphere? The temperature decreases to about minus 85 degrees C at mesosphere. And most meteors burn up in the mesosphere. And about the thermosphere, which is above the mesosphere. And the thermopause is about 500 to 600 kilometers in altitude. And this region, that's the thermosphere, is bombarded by extremely short-wave radiation from the sun and polluted by ionized atoms, which align with the lines of the force of the Earth's magnetic field. This ionization of oxygen and nitrogen releases photon, which may be visible to a aurorae. So it's called the northern light. So we know how the pressure and the temperature changes in different layers of the atmosphere, and then people propose the International Standard Atmosphere, the ISA. The ISA is a standard atmosphere to define the conditions prevailing for most of the year for aircraft operating up to an altitude of about 100,000 feet or 30 kilometers in temperate latitudes. That's, for example, the European and North America. And we can see the International Standard Atmosphere is tabulated in this way. So we can see the first column is altitude, and then we have pressure, temperature, density, dynamic viscosity, and the speed of sound. And also I highlighted there are several relative pressure, relative temperature, and the relative density and the relative quantities. So they are defined. These relative parameters are defined. For example, for the pressure is relative pressure is the local pressure divided by the pressure at sea level. So that's the definition of relative parameter.